Good morning, everybody. If you are watching this, I am assuming that you have completed the independent events investigation. So hopefully a little bit of what I'm going to go over with you all is going to be familiar. Now, when we're talking about independent events are events that do not rely on each other. Like you think about somebody being independent, that is somebody who does not rely on other people for whatever the context is. So independent events are events whose probabilities will not affect each other. So for example, for Mr. Price, an example of independent events would be if it's raining outside and the probability of me eating a sandwich. Like it raining outside and it not raining outside will not affect the probability of whether or not I will be eating a sandwich. So through that investigation, my hope is that you all have gotten that the way that you calculate independent probability. So if you're going to calculate the probability of A and B, you simply do that by multiplying the probability for A times the probability of B. So we're in page 261 for this example. So if you want to look at that, you're welcome to. If you would rather follow along with me, that's perfectly fine as well. So we've got a coin is tossed and a dice is rolled simultaneously. Determine the probability of getting a head and a 3. So what we've got to do that, the probability of getting a head and a 3 is just going to be probability of heads times the probability of getting a 3. So probability of getting heads on a coin is 1/2 times the probability of getting a 3 on a dice is 1 out of 6. And if we multiply those together, we get 1 out of 12. A 1 in 12 chance of that occurring. It's also worth mentioning that you could just make a diagram for that, or you could just think about that and select your outcome from that. But we're going to be trending towards multiplication today. So the next example here, we've got Carl's car. It's pretty unreliable. It will only start 80% of the time. And he's got a motorbike that will only start 60% of the time. And we want to know, okay, first off, can we use a diagram to illustrate this? So we've continued to look at different ways to illustrate probabilities. A way that we've used before is a tree diagram, so that's what we're going to use here. So the branches for this tree are, we've got this car one, so there is a 0.8 chance that his car will start. We're just going to say C. And there is a 0.2 chance of C prime, or just the complement of C. Because if there's an 80% chance that it will start, there is a 20% chance that it will not start. So then from there, we've got to say, all right, well, those are the odds for the car. Here is for the motorbike. So the odds of the motorbike starting are 0.6. So that's for M. And then there is a 0.4 chance for M prime. And same thing here, 0.6 for M and 0.4 for M prime. So there's 4 options that we can have for this tree diagram. And so we want to use, we have an illustration of those outcomes. And so we want to find the probability of both starting. So for the probability of both of these things starting, we would have to take the probability of both of them starting and multiply those together. So the path that we're really highlighting here is 0.8 and then to 0.6 on that tree diagram. So for both, it's as easy as these are independent events. Whether Carl's car will start does not affect whether the motorbike will start. So for both, we would have to do 0.8 times 0.6, which gives us 0.48. So there's a 48% chance that the bike and the car will start at the exact same time. So then the chance that the car would and bike wouldn't, so we can denote that with C, and that the bike would not is M prime. So I guess if we want to use probability notation here, excuse me, that is just terrible. Let me rewrite that. Probability of C and M prime. We're going to calculate that right there by doing the probability of the car starting, which is 0.8, times the probability that the motorbike doesn't start, which is 0.4, which is going to give us 0.32. There's a 32% chance of that outcome occurring. And what I want to illustrate to you all is all of those possible outcomes that could occur. If you add those outcomes up together, they should sum up to what? And hopefully here in your head you're saying 100%. All of those outcomes, the cumulative probability should always add up to 100%. So we're going to switch gears here from calculating independent events. Actually, I lied. We've got one more that we're going to do. Tricked y'all. Tricked myself as well. All right, so we've got Liam rolling a 6-sided dice. Determine the probability that exactly 1-4 is rolled. So we have to count the scenarios here on which he could get 1-4. So for 2 dice rolls, there are 6 outcomes for the first one, times 6 outcomes for the second dice. So for the first dice, there's 6. For the second dice, there are 6 as well. So that's for a total of 36. So then what we have to do now is think of the different possibilities here for getting a 4 when you're rolling a dice. So you could get the first roll could be a 4, and that could meet our condition. And then you need to think to yourself, how many possibilities are there for the second roll? If you have 4 on the first one and we want exactly 1-4, there you could get 4 and a 1, you could get 4 and a 2, 4 and a 3, 4 and a 5, 4 and a 6. We can't get 4 and a 4 because we're looking for exactly 1 dice roll. So these are all possibilities, but we could also go on the first and the second here. We could go 4 for each of the second dice rolls here. And then the first one, we'd hit all those possibilities. So it's basically a flip of what we've got there on the right. So in total here, we've got 10 possibilities. And there are more ways to do this. If you look inside of the book, you're going to see that they made a tree diagram to do so. I think it's important for you all to see that there's a lot of ways to tackle these probability problems. And so we'd write this fraction. There are 10 outcomes out of 36 total, and then we're going to reduce that fraction right there. So you can take a 2 out of 10 and a 2 out of 36 to make that 5 out of 18. And the reason I did not use a tree diagram, I want to try to expose you all to as many different ways of doing these as you can. If it asks for a tree diagram, obviously use a tree diagram, but I wanted you all to see a different way. So now we're going to switch over and look at dependent events. So for dependent events, those are events that directly affect each other. They directly tackle or they directly work with one another.